Right. So we'll discuss the stability of molecules, that radioactivity thing. So here also I will be just, going through the stuff and trying to uh, refresh your memory, right? So first of all, you need to remember about the nucleus anatomy. So these are some chemistry mechanics also, right? So just go through it. So you need to know where you can find the protons, neutrons, electrons, and here comprehensive summary is given there, right? So if you are dealing with protons, the mass, the relative mass is going to be 1 and the charge is going to be +1. Likewise, the most important stuff are given there, right? So here then the notation, so this is pretty much important, right? So if you get the notation wrong, then the whole question will be having a different approach, right? So remember what is meant by the atomic number, the mass number, and how you can deduct the number and get the number of nucleons, like those terms, right? So the isotopes and all the stuff is given here, right? So go through the note, try to memorize them. And the next one, so when it comes to radioactivity, we know that, so we are dealing with, there are some particles, but mainly we are dealing with alpha, beta, and gamma, and also neutron ejection as well, right? So those are the most important ones. So when it comes to alpha decay, decay means like removing, right? So no need of remembering these equations, right? Where you are going to deduct 4 from the mass number or something like that. Just remember the symbols of these particles, right? So if it is alpha, then the symbol is going to be 4 plus 2. And if it is beta minus, it is going to be 0 minus 1. Neutrons, it is going to be 1, 0. And if it is gamma, it's going to be 0 and 0. So these are the 4 particle symbols that you need to remember. So the upper number, it represents the mass, and the lower number, it represents the charge value, right? It represents the charge value. So just remember these symbols, then easily you can get what is going to be uh, generated as a product, right? So otherwise, there are so many particles, right? And there are so many equations to be memorized. So that is not a practical thing, right? So better to remember the core particles, their symbols, right? Remember the particles and their symbols. That's enough, right? Then you can easily get the final product from these ejections, right? Okay, then the alpha, beta, gamma, their nature and the typology, right? Or the factors, the characters are given here, right? So alpha can be written as nucleons and nucleus, beta, electrons, gamma, electromagnetic wave, neutron is going to be a particle. So here the ionizing power is given as a, like, something like a graphical explanation. So remember uh, the penetrating power, right? Or the distance that can be traveled, right? Penetrating power is inversely proportional to the ionizing power, right? Is inversely proportional to the ionizing power, which means if you are having a higher ionizing capability, then it has a lower penetration power. See, so here a higher power, but the penetration power is low, right? But here ionizing power is low, but the penetration power is higher, right? So don't remember it like these graphs, just remember the relationship, right? The penetration power is inversely proportional to the ionizing power. Penetration power is inversely proportional to the ionizing power. And here the shielding is given. So this is pretty much important, right? So you can block alpha radiation by just placing a small paper in the path. And for the beta radiation, it will be blocked by using a sheet of aluminum, and for gamma radiation, it will be blocked by several feet of concrete, right? Several feet of concrete. So there was a good question given from this table as well, right? So from the shielding part, right? So better to go through it. There was a question, as I can remember, in 2025 November paper, or some recent papers, right? I can't remember the exact year, right? Then the background radiation and the landscape. So you need to know what is meant by the background radiation. So if I explain it simply, the background radiation is the so here there are some, like, the components of background radiation is explained here. So we all know that, like, the how the universe expanded and how the universe, like these solar systems were made and so much of these things, right? So when there's an explosion, so there will be different sort of radiations emitted. So those radiations will be embedded in these systems, right? Embedded in these what do you call these objects actually, right? So food and drink, they will be containing different sort of radiation, and there will be like radioactive rocks in the in soil, right? And also there will be cosmic rays and medical sources. So we know that X-rays are also falling under different type of a radiation, and the nuclear sites, right? So if you remember this diagram, I think you can easily remember what are the sources of background radiation, right? So, and also remember, there was a question as well. So, in order to get a radiation measurement, then there must be a background radiation correction as well, right? Background radiation correction as well. So, we'll discuss about it. So, yeah. And the activity and the detection. So, activity is measured in becquerels. No need of remembering these terms, just remember the unit, right? So 1 becquerel equals 1 decay per second. And in order to identify this decaying process or the radioactivity, we are using photographic film, or most of the times we are using the Geiger-Müller tube, right? So here, Geiger-Müller tube, you need to know how it works. The reason is, like, it is given in the textbook, so they can ask a simple summarized question from the Geiger-Müller tube. So how it is going to be working, right? And the half-life constant, before going into that, I'll discuss about how to do that background radiation correction thing. So just imagine something like this, right? So let's say you are taking a reading from the GM tube, right? So this reading will give you the value of the radioactive sample plus the background radiation. So combination of these two, I will take reading one, or we'll say, yeah, this is going to be reading A, the value A, right? So we do not need this background radiation. We need only the pure samples radiation value, right? So we need only the pure samples radiation value, right? So in order to do that, what will we do is that we are going to enclose this sample, right? So this is emitting radiation, different sort of radiation, but we are going to contain it, right? So in order to contain it, we can use lead or something like those blocking material, right? Then, so now the radiation is trapped inside this box, right? Now we are going to take the GM tube, right? Now we are going to take a reading, right? So now this will give only the background radiation, right? So we'll take, this is going to be the reading B, right? This is going to be the reading B. So finally, the samples value, right? So in order to get the samples value, what we can do is we can deduct reading A and B here, right? Now you will be getting only the samples reading, right? So remember this, there was a question from this section, right? How to get the, how to correct the background radiation effect. Okay, so this is the process that we are using. Okay, then the half-life constant. So half-life means, right? Remember, you are having a sample. Let's say uh, the radioactivity or the concentration is R now, and now the concentration is half of that value, or not over 2, half of that value. So the concentration of the radiation deducted by 50%. So in order to deduct it, the time consumed. So that is known as the half-life value, right? That is known as the half-life value. So definition, Half-life is the time taken for half the unstable nuclei to decay, or the time taken for the activity to be half, right? So the core principle is the decay is random, right? So even this thing was tested in the exam, right? Remember, decay is random. We cannot predict it, right? We cannot say like it will be like, a uniform one, right? It will be random, but half-life is constant. So the time to half remains identical regardless how many of nuclei already have been decayed, right? So when it comes to this half-life constant, so it will actually depend on the reaction itself, right? So you will learn about these things in chemical kinetics in your A levels, right? But for this level, just remember half-life is a constant, and you will be getting a graph like this, right? So if I explain the graph, so here you can see, right? Starting value is 80, right? Starting value is 80 at the time of 0, right? And it drops to 40 here. So which means here now it is 50% reduced, right? Starting from 80 to 40. So the time taken for that is 2 minutes. So which means this is going to be the 2 days actually, right? So this is going to be the half-life. And if we further analyze it, so now it is at 40 and now it is at 20. So which means here also again dropped by 50%. So the time, so from 2 days to 4 days, which means the half-life again 2 days. And if we further analyze for the third one, then it will be here at 10, 50% drop. So the consumed time would be 6 days, right? The consumed time would be 6 days. Likewise, you can analyze it, okay? Then the hazardous diagnostics. So irradiation and the contamination, you can go through them, right? There were so many questions from this contamination and irradiation and the meanings and all the stuff, right? So you can go through it. And engineering the applications, no need of going through this one. Yeah, no need of going through this one. And the medical applications of radiation, right? Why we are using it and what are the most important stuff. So just try to remember one or two, right? That's enough. Okay. Then the nuclear fission and the nuclear fusion part. So nuclear fission, right? Nuclear fission means we are like, the nucleus is being broken, right? So here this is very unstable process, and you can get a huge amount of energy from here, right? So here you can see the process is given. The thermal or the slow neutron will be attracted or will be bombarded towards the 235 uranium nucleus. So then it will become what? Here neutron is being added, so then it will become uranium 236. So this is very unstable, right? So this is very unstable. So therefore, what will happen? It will again broken into their daughter nuclei, right? Daughter nuclei. So daughter nuclei will be again 235, uranium 235, having what? A neutron, right? Having a neutron. So likewise, the chain reaction, the reaction will continue, right? So in order to harness this energy, so in this sort of reaction, there will be a huge amount of energy released. So in order to harness this energy, we are using the nuclear reactors, right? So we discussed about these things. No need of remembering the diagram, but just go through it, okay? So here we are using control rods. So remember what are the materials that we are using and what is the reason for the control rods and the coolant, right? What is the reason and why, what is the most appropriate coolant, the solution that we can use, like why are we using water, right? And is there any sort of any alternatives, right? And the moderator, the reactor core, right? And the containment wall. Why can't we use any metal there, right? So go through it. There were so many questions from this sector, right? So go through it, try to remember what are the uses and the materials that we can use. And then the nuclear fusion. So this is the opposite version of the fission. So in fission, we are going to break the atom, but here we are going to fuse the atom. So fuse different parts into a single one. So here hydrogen 1 and hydrogen 2. So this is protium and deuterium, and this one is tritium. No need of knowing the name. So you are going to combine small atoms and into a huge one, right? So here fusion powers the sun. So it is the process of forcing two light nuclei to fuse into a larger nucleus accompanied by massive release of energy, right? So the energy released by fusion is larger than the energy released by the fission, right? So remember that point. It requires extreme temperatures and pressures. So normally on the sun, we can see on the surface of the sun, we can see the nuclear fusion reactions, right? So, but in normal conditions, the normal conditions that we are using in nuclear reactors, we cannot allow fusion to be occurred, right? The reason is like it is requiring huge amount of extreme temperatures and pressure. So we cannot make it happen, right? So the barrier is we cannot easily replicate this on Earth because overcoming an immense electrostatic repulsion. So remember this one, right? We need the stellar level energy. So it requires a huge amount of energy. And here a summary is given, right? Spontaneous decay means the radioactive things, or spontaneous means like in an uncontrolled manner, right? So either there can be beta radiation or likewise, and nuclear fission and nuclear fusion, and here it is given. So the most important parts here is the nuclear reactor thing, right? And also here you need to know what is meant by a chain reaction, right? What is meant by a chain reaction. So this is a good example. So try to go through the textbook or the theory notes, and you can easily remember what is meant by a chain reaction. So if they are asking any sort of examples, you can use this example, right? So uranium-235 treatment with the neutron thing, okay? So go through it. So that is not included in these lecture slides, the chain reaction part. And remember the medical appliances and also some harmful effects as well, right? Harmful effects as well. And there was a good question from this irradiation and the contamination part. As I can remember, they were referring to some sort of a food. I can't remember, apples or something like that. They were radiated with gamma radiation in order to in order to protect them from infections or something like that. So they were asking whether is it good to eat these food or something like that. So go through that question as well, right? And half-life also. And as I need to mention, most of the time there will be a half-life calculation. And also remember, just try to use the flowchart method as possible, right? Use the flowchart method. So we discussed so many things about this flowchart method in the theory classes. Uh, the reason is that I gave you an equation, but keep it as a second option, right? So try to use the basic theories and try to get the answer by using the flowchart method. If not, then you can go for the second option, right? At least we need 1 mark for the final answer. So therefore, you can go for the second option, but your first option must be the flowchart method. So keep that in your mind, okay? Your first option must be the flowchart method. Then, yeah, we discussed about how the background radiation can be corrected and go through the Geiger-Müller tube, right? And the background radiation scape, the radiation things, and this table is also important, right? And this one as well. So here you will be using this one in order to write the reactions, right? So go through them. Those are some easy marks actually. So normally if they ask a reaction, so it will be contributing just 1 or 2 marks, most probably two, right? So uh, go through the questions as well, right? And there's another thing. If it is like here, just imagine there are 3 alpha radiation were emitted, then this number will be reduced by 12, and this number will be reduced by 6. So you need to multiply by 3 here, right? You are reducing 3 alpha radiation. So therefore, 3 times of the mass will be reduced. So remember those points, they were also tested in the exam, right? So these are some simple stuff, okay? And yeah. So that is the end for this section as well. Uh, I rushed through this stuff because already we have discussed and already we have completed the paper classes and all the paper discussions as well. So there's no need of like taking 2 hours and repeating myself once again. So there's no need, right? So it is going to be boring or something like that. So yeah, tell me whether you are having any sort of problems related to this stuff, any sort of questions. Yeah, beta plus radiation. So it will be the what do you call that? The opposite version of the beta minus, right? So if you are using beta minus, then beta plus means mass stays the same, but the charge is going to be plus one. Now it is going to be changed, right? Instead of minus one, then you are using the plus one there. Uh, that's the only difference there. That is the only difference. Yes, any other questions? Don't just remember these equations, whether if it is beta minus, then you need to add one for the atomic number. Don't be like that, right? Then you will be like machines. Then there's no end of like, memorizing these equations or something like that. So that is not the point. You need to grab the theory and according to that, you need to apply it, right? So remember, so in this case, if it is beta minus, then this Z value is going to be minus one, right? You can do the calculations and see, right? So we did so many calculations based on these things. Please go through them, right? So as I'm mentioning all the time, uh, there's no need of going through like, reading theory notes or the textbooks once again. Just go through the calculations that we have done. Go through the questions. That is the most important part. That's the most important thing, right? So you can like at least refer the question with the marking scheme, right? Read out the question, then refer the marking scheme, right? So likewise, you can increase at least by 1 or 2 marks, right? It will be like you can use that method for any other subjects as well, right? So go through the notes, go through the question papers. That is the most important part. So we are like, pretty much close to the exam. So please utilize this time. So I won't be taking more time from you guys. Please utilize the time and give your maximum effort in this. Okay. So I'm going to conclude the session and if you're having any trouble, just drop me a WhatsApp message and I'll help you guys out. Okay. So thank you for joining and try to utilize the time as possible. Okay. Okay. Thank you.